Assalamualaikum. Today, our group will present about insect classification using image processing and deep learning, which is CNN. First of all, this is our team member. The first one is Shahra Zaman. The second one is Muhammad Aiman Hafiz. The third one, Nuriana. And lastly is me, Nasha Farina Izzati. Insects are an important component of the biodiversity of our planet because they have evolved to withstand almost every type of environmental stress from the beginning of life on Earth. Accurate identification of insect species is crucial for conservation. Using image processing techniques such as denoising and sharpening, we improve image quality for high-quality datasets. Combining this with a deep learning, specifically convolutional neural network, we aim to develop a faster, more accurate insect classification system. This will enhance scientific research and practically applications leading to better biodiversity conservation. So, for the adjective, the first one is to use image processing techniques to enhance the images of insects. The second one is to use convolutional neural networks in a deep learning technique to classify insects. And the last one is use OXU thresholding for effective image segmentation and create a lightweight model with insect prediction capabilities.
And now, I will present about the project significance. To significantly enhance the accuracy and efficiency of recognizing insect species, this research integrates OXU thresholding, CNN, and image enhancement techniques to provide a strong framework for insect classification. The approaches and results can lead to improvement in entomological research and also environmental monitoring. For entomological research, when we are using to accurately identify insects, scientists may more thoroughly examine ecological relationship, trend, and biodiversity. These technologies speed up data collecting and processing, making long-term monitoring and broad ecological research easier. For environmental monitoring, the CNN power system allows environmental experts to keep an eye on the health and variety of insects. Because it makes it possible to identify and react to environmental changes more quickly, this trustworthy data support ecological study and conservation.
I'm Norena Midiazid and now I will present about the methodology. The step-by-step procedure used in insect classification have shown in this flowchart. Our process begins with identifying the types of insect we want to classify, which is cicada and also the snail. We compile a list of different insect categories. For each type of insect, we collect a substantial number of the image. These images are then organized and inserted into our working directory for further processing. The goal of the project is to identify different insect species using a data set of 25 test images and also 25 training images. The images are first acquired and pre-processed. This step includes tasks like resizing image to a uniform size and converting them into a suitable format. Enhancement techniques are applied to improve the quality of the image, such as adjusting the brightness and also the contrast. Non-local means denoising is used to remove the noise, and also Gaussian filter are used to smooth the result. Next, images are segmented to isolate the insect from the background, which help in focusing on the feature of the insect. The improved image is then transformed to grayscale, which reduces the image to shade of gray and simplify the processing. Also, thresholding technique also is used to minimize the intra-class variation and find the ideal threshold value that divide the pixel into two groups. Using this technique, pixels may be classified into foreground, background to create a binary picture. These features are essential for training the CNN model. We then develop our CNN model architecture tailored to the classification task. The model is trained using our preprocessed and segmented dataset. For the training, we use 3 layers of convolution with Mac epoch 10. We use 10 times for the training, and during this step, the model learns to recognize patterns and features specific to each type of the insect. After training, we evaluate the model performance and on the training dataset. If the accuracy is not satisfactory, we iterate on the model, tweaking parameters and architecture until acceptable performance is achieved. Once the model achieves sufficient training accuracy, it is safe for further testing. The same model is tested on a separate dataset to evaluate its generalization capability. Finally, we assess the prediction accuracy of the model to ensure it performs well in real-world scenarios. To sum up, this workflow ensures a structured approach to developing a robust CNN model for insect image classification. By following this step, we can systematically improve our model accuracy and reliability.
For the dataset, the input data consists of two types of insects such as cicada and snail. Our dataset has a total of 100 images and it is divided into 50 images of each type. We use 80% for the training and 20% for the testing, which means 40 images for each type are used for the training and 10 images for each type are used for the testing. We did pre-processing to the image such as labeling, removing the background and resize for the image. For the Kikada datasets, we are labeled from C1 new to C50 new, while for the snail dataset are labeled from S1 new to S50 new. This is the dataset for Kikada and snail after the enhancement. A number of methods are used to enhance the quality of the image. We use non-local means denoising is used to remove the noise, and the Gaussian filter are also used to smooth the result. Sharpening technique draw attention to the crucial details, while adaptive histogram equalization improve the contrast. Adjustment are also performed to brightness and contrast to make sure the image appear consistent and realistic. For the segmentation data, we use segmentation to separate the region of the interest, which is ROI, or more precisely the areas where insects are present. Segmentation is used. There are several complicated steps in this procedure. In order to make the insect stand out more clearly, the image is first improved to increase its quality, which is we use the enhancement method. This may involve altering brightness and contrast or using filters. The improved image is then transformed to the grayscale, which reduces the image to shade of gray and simplifies the processing. This is our training data. We use the highest accuracy for the training for the image submission. We use the segmentation image to train the neural network, which is CNN. To achieve this result, we change the convolution layer, we change the learning rate, and we also change the epochs to make the highest accuracy. For the testing phase, we use a CNN as our testing method. There are three crucial layers contribute to feature extractions, which is convolution. Convolution layer employ learnable filter, which is kernel to detect local patterns in input data. Through element-wise multiplication and summation, this filter extracts specific feature enabling the identification of the age, texture, and visual pattern. The ReLU layer introduces non-linearity by converting negative value to zero, enhances the network ability to learn complex relationship in the image. Relative linear unit, which is ReLU. This activation function enhances the network capacity to learn and represent interrelationship in image by introducing non-linearity. Negative value are simply changed to zero, removing black from the image. Next is pooling. Pooling layer reduce the features map of convolution layer, retaining valuable information while reducing spatial dimension. This made the network more resilient to input variation like shift or distortion. The output of the feature extraction serve the classification task involving additional layer, which is flattening layer. Flattening layer convert multi-dimensional features map into one-dimensional vector, preserving spatial information for a traditional neural network structure and enabling one-dimension input, fully connected layer. The flattened this process flattened feature vector through fully connected layer, where each neuron is connected to the previous layer. This layer learn and map high-level features to output classes or categorize using a weight sum of input and an activation function, ultimately making the final classification decision. Following the training phase, a CNN is ready for the testing or interference on a new previously unknown data. The trained network processes the data to produce prediction or classification. To ensure robust and efficient testing, our system follow a multi-step process, which is data preconditioning. The image are prepared for the network input using technique like resizing, which is we use 600 times 600 fixture for the insect classes, normalization, and potentially data augmentation. The specific processing depend on the data type and the network architecture. For the forward propagation, the pre-processors test data, we use 100 image in this case is fed through the network layer sequentially, including convolution, pooling, and other layers. Each layer performs its specific function on the data, extracting feature and gradually building a representation for a classification. For the next one is the performing evaluation and optimization. We conduct iterative testing with various network configuration. This involves adjusting parameter like the number of the training files, adding or removing features classification layers, modifying the learning rate and experimenting with different dataset size for the training and validation. The goal is to identify the configuration that yields high accuracy on the data set.
For the result, we can see the table provide the recognition rate for the insect considered in the experiment. For the experiment, we use the type of insect such as cicada and snail. Using this data, we can calculate the overall recognition rate, which is determined to be 96.11% for cicada and 100% for a snail. This high level of accuracy demonstrates the effectiveness of the pre-processing technique and the strength of the classification algorithm used in this study. The result confirm the approach and highlight its potential use in real-world scenarios for insect recognition tasks. For the conclusion, we can see this project use image processing and deep learning (CNN) to classify cicadas and snails with high accuracy. From the testing result, we can see we have achieved 96.11% accuracy for cicadas and 100% for snails by enhancing image quality, segmentation image effectively, and training an image using CNN. We simplify interclassification. This method supports environmental monitoring and entomological research by providing a precise and scalable solution for insect classification, overcoming the limit of manual identification. That's all from us. Thank you.